Welcome back. Now I'm going to be doing a demo on transformers. In electricity, we learned that transformers is a very important device. It can take an incoming AC source with a certain voltage, and it can step up that voltage or step down that voltage. This is used a lot in modern technology. The power companies deliver power at a certain voltage, and then they step it up across very long electrical lines. They step up the voltage so that the current will go down. So they deliver this power at very low current, very high voltage across these long power lines, and then they step down the voltage when it comes back to our homes. They step down the voltage to whatever our voltage in our homes is, either 120 or 220, depending on what country we live in, right? So the transformer that we have an AC source. In order for this to work, for the transformer to work, you have to have AC. So the AC is going to be connected to, and then the basic model of a transformer is that it has a coil, let's say a certain number of turns, right? And then the coil, there's some kind of iron rod, something linking it to another coil, like this. And then maybe this one has less coils. Okay, so then you go like this, and then this is the output. Okay, and then I can measure the output voltage with a voltmeter. Right? So what's happening is that when an AC source is coming and producing AC current here, the AC current is constantly changing, which is creating a magnetic field, right? That magnetic field, what will happen, that magnetic field will link itself to the other coil, like this. So the reason that they put an iron rod to connect the two coils is that the iron rod will strengthen the magnitude of that magnetic field and will link up the magnetic field lines of this coil to the other coil so that the magnetic field doesn't leak out. So when you have magnetic field lines leaking out of the transformer, then the efficiency of the transformer goes down. The stronger the magnetic field line and the more the two magnetic field lines are connected between the two coils, then the more efficient the transformer will be, and its efficiency will be high. Right? So then these magnetic field lines will link up like this. Okay? So then what happens is that the equation governing this is that the output voltage divided by the input voltage is equal to the number of coils of the output over the number of coils of the input. Okay, so I have here with me, okay, I have here the power supply. This is the power source that I'm going to use, and then this is the transformer. So you can kind of see here how the iron rod connects the two coils. This coil has 400 turns, and then this one has 600 turns. The red one is 1600 turns, so it's 4 times more turns, and then this is 400 turns, right? So if I want to step down the voltage, I'll put the input voltage into the higher turns, then I will determine what the output voltage is in the lower turns. So now let me put this on 6 volts, my power source, 6 volts. Then I'm going to measure the incoming voltage. So this one is DC, this one is AC. In order for the transformer to work, it has to be in AC mode. Okay, so I'm going to put AC here. Okay, then I'm going to put this on my voltmeter. Okay, so I'm just going to put this on volts. Okay, then I'm going to put this here, also on the common outlet. Then I'm going to measure the voltage here, put it on AC. Okay, so this one I have it on 6 volts, and then this one is showing 6.62 volts. So my incoming voltage is 6.62 volts. Let me write that on the board. What am I going to do? How am I going to connect this? So then I'm going to take the voltmeter. Then I'm going to take the power source. Then I'm going to go into the higher number of turns. I'm going to put it into the 1600, right? And then that's going to link up to the 400, and then the 400 I'm going to connect it to my voltmeter. Okay, so I'm going to put it here across the voltmeter. So I'm going to see what the output voltage is. So the input voltage, remember, was 6.62 volts. The output voltage is 1.196. 1.196, you can see here. So it went down. So let's see how much down it went. 1.196. Now, theoretically, the output voltage was supposed to be what? The output coil was 400, and the input coil was 1600. So the voltage should have gone down by 1/4. So this is going to be 1/4. So the output voltage was supposed to be 1/4 of 6.62. So let's calculate what that is. But what was the actual output voltage? 1.196. So we had a loss of voltage here, and therefore we had a loss of power. What happened? All the magnetic field lines that is produced by this coil did not go into that. What ended up happening? Some of the magnetic field lines went outside in the other direction. And therefore there was, think of this almost like loss of information. The changing current here is supposed to be producing a changing magnetic field, which is supposed to be producing a changing current in the other coil, which is supposed to be producing an AC voltage, right? But not all the magnetic field here is going there. Some of it is being lost. So that's producing an inefficiency. So we can calculate the efficiency of our transformer. We can divide the actual output voltage divided by the expected output voltage. So the efficiency is going to be 1.196 divided by 1.655. Okay? So then I'm going to do 1.196 divided by 1.655. That's going to be 72.3% efficient. Okay? It's not bad. Pretty good. 72% efficient. But hopefully, if you buy a more commercial transformer, hopefully that is going to be a higher efficiency. Now let's test to see whether the efficiency of the step up is better. We're using it as a step down transformer, right? Step down. Why? We are stepping down the voltage, right? We're stepping down the voltage. Now if we want to step up the voltage, the opposite will be true, right? Okay, so now I'm going to have the same input voltage, but the only thing that I'm going to change is that this one, let me take the voltmeter out of the equation. So then the power supply, instead of going into the 1600, is going to go into the 400. It's going to go into the 400, so it goes right here, right? And then so this one has more coils, and so therefore the output voltage should be higher than the input voltage, right? And in theory, it should be 4 times higher. So then I'm going to connect this side to the voltmeter. Okay. And then the voltmeter will measure, you can see here, 21.92, 21.91 volts. So it has been stepped up, 21.91. So now let's actually measure the efficiency of that, right? And therefore my efficiency is what now? Notice now that the output voltage is not actually as much as it's expected to be. So again, there is loss of information, and therefore the efficiency is not 100%, right? So efficiency is 100% times 21.91 over 26.48. So we do that. 21.91 divided by 26.48. 83%. So 82.7%. So just from that simple experiment, it looks like the step up voltage is more efficient, right? That kind of makes sense, because if you think about it, it is more efficient to raise something than to lower something. Like if a car is pressing on their gas pedal, it's easy to transform that to the motion. But if you're now going to try to stop the car, you're going to have to press the brakes. You're going to have to try to slow the car down. You're going to have to go down in the energy, in the kinetic energy of the car. It's less efficient, and more energy is lost to heat in the brakes. Less energy is lost to heat in accelerating the car, right? So it seems like that could be like a general thing, to step up the voltage is easier than to step down the voltage. So it's 82.7% efficient, whereas stepping down was 73% efficient, right? Now I want to show you quickly that this only works if you have AC circuit, right? And I put it to DC output, right? DC output. So let me show you here what is the original output voltage. So then, if I'm having it on DC 6 volts, I'm going to put it on this common and volts ohm outlet. Then I'm going to put it on DC voltage of the voltmeter, right? Not the AC voltage. The AC voltage is the one that has this little wiggly line, meaning that it measures AC volts. Now you're going to measure DC volts. So it's showing 6.35 volts DC, right? Then I'm going to take this and put it to the 400, right? And then from the 1600, I'm going to go into my voltmeter. Right? And nothing. No voltage is produced. That means this mechanism of stepping up doesn't work. Because what happens is the incoming current that is in here creates a magnetic field, but that magnetic field is not changing. Therefore, it doesn't create a current here. And if it doesn't create a current here, the voltage across these two is zero, right? The only way that this can create a current here is if the magnetic field created by this changes. If it changes, then it creates a current here, which means there's a voltage difference here. So you see here, you can tell here, 0 volts. This is one big reason why we use AC instead of DC. This is a big story to this, a big history that you can go into and read about it. The whole history about the DC versus AC, and then you can also read about it, but you can see that this is a very important reason why we would use AC, right? DC, you cannot step down the voltage, you cannot step up the voltage, but AC you can, okay? So this is a good little demo illustrating the efficiency and then the usefulness of the transformer and how it can step up and step down, okay? Thank you very much.